Hello there, my hardy physics class. Here we are ready to embark on one of our very last topics having to do with thermodynamics, which we're going to take a look at as well as we can here, and looking forward to being able to wrap up everything that you need for this year. So thermodynamics having to do with the study of heat. So when we're thinking about physics, we had been talking in the last whole entire unit about mechanical energy and mechanics and how things have that energy stored up and they can use it. Thermodynamics, the study of heat. Heat is just another type of energy. And physics really deals with studying energy in many, many different forms. So thinking about this, what we can consider is that really basically one of the important things is that all of the heat that we think about comes down to having come from the fact that particles are moving, and without any movement of particles, there is no heat for us to study. Okay, heat is really related to that motion of these teeny tiny little particles, and the faster that they move, the hotter the substance is. And that whole idea of heat has to do with a couple things which we're going to delve into. And the formal name for that is the kinetic molecular theory, in that matter is made up of the tiniest little particles that are in constant motion. Now, you don't usually think of solids having motion in them, but solids do have motion at the molecular level as long as it has any kind of heat energy to it whatsoever. And you'll find that there's a lot more heat energy that is around you than you ever would have thought of. Okay, but so even in a solid state, there's a lot of vibration at the very, very smallest levels, and that's where we can study the heat, the thermodynamics that's in that. Okay, so thermal energy, or that heat energy that I've been talking about, is the overall energy of motion in a particle, in motion of particles that make up an object or a certain body of particles. So you could have a gas that is encased in a balloon, for example, and you could study the entire thermal energy of that particular system right there. So it's the overall energy of motion of those particles. That's different than temperature, because temperature deals with an average kinetic energy in an object. So it has to do with that energy, how much it is in just one spot, but it's not the overall amount of energy. So it's more of a measure of the heat, the hotness or the coldness that we think of. You touch something that has a higher temperature, we think of it as hot, and it has a colder temperature, we think of it as cold. And the temperature is just going to be measuring at that one spot rather than taking a picture of the overall amount. The overall amount has to do with how many particles and the heat stored in the whole body of it. The temperature is just how hot or cold it is in that one spot. And so it can have, an object can have more thermal energy in another one, even though it has a lower temperature, because there's simply a whole lot more of it. Okay, so for example, if you think about the whole ocean, even though it's not necessarily very warm as we think of as warm, if you thought about all of the ocean in the entire world, it's got a lot of thermal energy stored up in there, where you might have one little small something, or you may even take your own temperature and find that your temperature is warmer than the ocean's temperature. However, you're just very small, so you have less thermal energy in you than the whole vast ocean that has more particles in it. So we need to differentiate between thermal energy and actually temperature. Okay, so let's think this through for a minute. At the same temperature, 2 kilograms of steel will have twice as much thermal energy as 1 kilogram of steel. Well, okay, we have twice as much of it, and they're at the same temperature, so all the way throughout it has more thermal energy, so sure, it's got twice as much, so that one's true. Temperature depends on the number of particles in the body. Well, not really, because you can have something that has a high temperature or low temperature, and you're measuring that independent of how many particles there are. Okay, you can have the ocean, you're measuring the temperature of the ocean, and it has a whole lot more particles than a little glass of water that you would be measuring its temperature, but they could have the same temperature, so it really doesn't depend on the number of particles, so that one's false. And thermal energy depends on the number of particles and the temperature. Yeah, that's actually true, because you've got the thermal energy. There is more thermal energy if it's a higher temperature, if you're talking about the same amount of material. Okay, so that one's actually true. Okay, so energy can get transferred. That thermal energy can get transferred from one particle to another. And if it happens because of collisions, that's called conduction. Okay, so some heat transfer happens because of conduction. It's kind of like you're in a hallway and you've got a bunch of people, they're bumping into each other, so the energy would be getting transferred from one person to another person to another person. So if it's by touching, it's conduction. Okay, and so in our world right now, we're trying to minimize the contact. So the transfer of anything by conduction is meant to be minimized. Okay, so conduction would be the process of transferring particle by particle through collision. So when you get two bodies that are touching each other and they're at the same temperature, there's no transfer, or the transfer is equal from one to the other. So there's always heat being transferred, okay, from one to the other when they're in contact with each other. But if their temperatures are equal, then whenever some heat energy gets transferred to the one and then back, and then one and back and one and back, then as long as that transfer is equal in between them, we say that those two bodies are in thermal equilibrium. And that really is how a thermometer works. The thermometer tells you your temperature. So you have a thermometer that is at a different temperature than the inside of your mouth, and you put the thermometer in there, it comes into thermal equilibrium. Okay, in other words, it gets to be the same temperature as the inside of your mouth, and then it gives you that reading. Now, there are other types of heat detecting devices, the ones that don't work by touching. So this particular thermometer I'm talking about is the one by touching. So when a thermometer becomes in equilibrium with your body temperature, then it can tell you and give you a reading as far as the number that goes with that. So what about that number? In this country, we're used to a Fahrenheit scale. However, Anders Celsius developed a scale that you're familiar with, probably maybe not familiar with his first name or where he's from, but he developed this Celsius scale in 1741, and he made it very convenient. Because that whole 32 degrees Fahrenheit for freezing and 212 for boiling is just kind of a little awkward to use. However, Celsius scale, where you set 0 at freezing and 100 for boiling, well, those are two very important temperatures, so it just makes some good sense. Human body temperature is about 37 degrees Celsius, but we're so used to the whole 98.6 Fahrenheit, and we're even finding now that uh, overall body temperature has changed over the years, so we're now a little bit cooler than that. But um, for our purposes, we have our average human body temperature about 37 degrees Celsius, and this scale works fantastic for being able to do practical things, for seeing how close we are to the boiling point and the freezing point. The problem is with that scale is that when you try to use it in formulas that deal with temperature and you have this zero, the zero kind of messes up our temperature, our equations. So another scale had to be figured out. Okay, so the other scale that we figured out is called the Kelvin scale. Okay, and the Kelvin scale changes the zero down to what's called absolute zero, which is the lowest temperature that something can meet. Okay, so absolute zero, the lowest that it can get, and it makes it much more convenient for equations, makes equations work that wouldn't otherwise work. And that absolute zero is when, and it matches up more with the idea of heat because it is the temperature where all motion has completely stopped and there is no energy, no thermal energy whatsoever. So there's no more energy to remove. And there's no such thing as having negative energy. We have only a measurement of how much energy there is. So it makes sense that you would have a zero number where there is zero energy if you're measuring how much energy. Okay, so as far as an upper limit, there's not really an upper limit to how much energy that we have, but there can be a point, or there's a theoretical point where you have absolutely no energy. Now, no one obviously could survive at that, and even the dead things that are around us, the wood that's been made into tables and whatnot, there's still some thermal energy in them. They still have a certain amount of movement in the particles, and there's still some heat there. So this absolute zero is way, way, way below freezing. Remember, freezing, where the water turns to ice, is at zero. This is negative 273, so it's 273 degrees below that. So the scale that is more useful for us is the Kelvin scale. And I know that you've heard of this. This is probably a lot of review from your chemistry class, but just so that we get this, we would say that that absolute value is the number 0 Kelvin. Not degrees Kelvin, it's 0 Kelvin. We drop off the decimal places so that we say that 0 Kelvin is negative 273 degrees Celsius. And we use that to develop a very simple formula that you're going to use and do some conversions today and practice it. And so our interval is the same. This is what's convenient between the Celsius scale and the Kelvin scale, is that the interval is the same. Each interval, each Kelvin higher, is the same amount different as 1 degree Celsius. Okay, so if you know your Celsius temperature, you can add 273 to it to get your Kelvin temperature. Because think about it, negative 273 Celsius is the same as 0 Kelvin. Okay, so this is where this formula comes from. So you're just going to practice using a little bit on practice problems 1 through 4 in chapter 12. So you're going to work on those problems, and it's just some conversions back and forth between degrees Celsius to Kelvins and Kelvins to Celsius. So you would use that formula. The degrees Celsius plus 273 equals the Kelvins. So if we have the Celsius, you plug in the Celsius and you get 298 Kelvins. And if you have 245 Kelvin, you plug that in, you end up subtracting, and that's the same as negative 28 degrees Celsius. So the fourth question in the practice problems is going to ask you to do just some really quick Google searches, or whatever kind of searches you do. You can ask Siri or however you want to handle that, and just find out some common temperatures. Now, what you'll do is you'll ask Siri and it'll give you a number in Celsius, or you can ask Siri for numbers in Celsius and then do your conversions over into Kelvin, just so you have an idea of what some of these common temperatures are in Kelvin. And then when you've figured out what common temperatures are in Kelvin, it's going to give you an appreciation for why we use Celsius and why we have two different scales, because it just makes it easier for our minds to think about when we have convenient numbers between 0 and 100 to think about for most of our life issues. But then when you have to do some scientific issues where you have to actually measure heat energy, and we'll get to that over the next few days, then the Kelvin scale becomes more important for us. So all that being said, I'll let you get to your practice problems and have a very blessed day.